So I'm going to speak about the sedimentary systems on Mars and specifically about their mapping. First of all, I will introduce their geographical and stratigraphical distribution. Then we will go across some problems and peculiarities of their of working with these deposits, and then we will face the problem of the scales of mapping and the approaches in mapping. Then I will spend some time on the stratigraphy, because stratigraphy is always important, of course, but is specifically important for sedimentary deposits because they, sorry, I'm trying to okay, now it's better. Because it's the only way stratigraphy to move from the interpretation of the single landforms that we are going to see is always difficult and sometimes tricky, to the interpretation of associate landforms, so landscapes, which interpretation is more, in terms of genetic formation, of course, is more constrainable, so to say. Then at the end, I will show some examples, I'm afraid not complete, of some of the sedimentary systems that have been documented on Mars. Maybe this is not necessary, but since some of you are not geologists, I'm making this short introduction on the clastic sedimentary environment, which are the most diffuse that have been proposed on Mars. These are the ones that forms through a weathering and erosion from a source area, then by transport, by means of gravity or ice or wind or water, until they reach depositional environments where they are, of course, deposited, and then diagenesis transform the sediments into sedimentary rocks. These deposits are also called alloctonous because they come from a source area and they are deposited somewhere else in a basin which is different from the source area. Also, some evaporitic depositional environments have been proposed, actually sometimes proven even by rovers. Evaporitic deposition environments are those where the sedimentation occurs through direct precipitation of minerals inside the basin, such as, for example, in this case, we have an ephemeral lake and precipitation of salts. These deposits are called autochthonous deposits because they form in the very same place where they are deposited. Sedimentary rocks on Mars are distributed. In these maps, we see only the distribution across the high-resolution imagery. The white dots represent high-rise images, while the black dots represent mock images. And you see, of course, the distribution is also depends on the distribution of the images, but it's enough to see that sedimentary rocks are widespread basically all over the planet. So they are a very important part of the geological history of Mars. Stratigraphically speaking, the sedimentary deposits are basically widespread throughout all Martian history, but the water-related ones, for example, valley network, outflow channels, and of course, incision of canyons, sulfates formation, are constrained within the Noachian and the Hesperian. Later on, we have a lot of glacial deposits forming during the Amazonian. The polar layer deposits are forming even now, just like Aeolian deposits, dust, but also dunes that have been shown to move even today. But I mean, for most of what I'm going to say in the next slide, I will stick to this part because it's the most, I mean, significant one, so to say. From the point of view of the mineralogical, the sedimentary mineralogical evolution, Lucia already told something about this, so I will not go into the details, but the sedimentary history of Mars starts with clay-bearing deposits, which depict a water-rich early Mars, also with the association of possible sedimentary carbonates, even if they were very minor deposits. Then from the late Noachian, these clay-bearing deposits are associated with intermittently sulfate-bearing deposits. And this depicts a scenario where water is increasingly limited, maybe local, especially at the end. Then from the Amazonian, basically, the conditions became hyper-arid with extremely few water, just localized in time and in space. And basically, we have the deposition of ferric iron oxides. The Mars sedimentary deposits are important. Okay, first of all, sedimentary deposits are not so common in planetary settings, and Mars is an exception. So are important because they are widespread, they are diversified, especially in early Mars, I told you that. And also they are important because Mars sedimentary rock has similarities, but also differences from Earth. And of course, we need the comparison from Earth with Earth. I will show this later to properly interpret the sedimentary environments on Mars, but also Mars sedimentary deposits have been historically important to better understand some this was the case, for example, of the outflow channels that we are going to see later. But apart from this historical perspective, sedimentary deposits on Mars are the key to understand the environmental and climatic changes on the planet, and they are important for their implications on the habitability potential. And the last missions to Mars are specifically devoted on these two science topics. Of course, if sedimentary deposits are important, it's important to mapping them. This is actually true not only for sedimentary deposits, it's important for all kinds of planetary surface from Earth to everywhere. This because geological maps are the only tool to assess the geographical distribution of a given unit, but especially because they are the only tool. I'm sorry. Sorry, I was not able to upgrade my brain with my new fancy mouse. So sometimes I have this jump. I apologize. I was telling that the sedimentary, the geological mapping is not the only tool to assess the geographical distribution of a given unit, but they are the only tool to assess the vertical and lateral relations between the different units. And this is very important. Of course, geological mapping, again, not only of sedimentary deposit, I would say of all planetary surface, has some problems and peculiarities. First of all, the scale of the mapping depends on the instruments that we have available. Even on Earth, we have geological maps at different scales. Marco 2 days ago showed beautiful examples of geological mapping at very different scales. But on Earth, when we go to the field, we observe the outcrops, we measure, we took our note, and at the end, we decide which kind of scale to use depending on our science goal or whatever. On Mars, on the planets in general, it is different because we can observe only what the instrument allows us. So, and this can change from place to place in the very same area. So this is something we have always to be aware of. Then we have a remote sensing method, of course, with no or very limited ground truth. We have very few rovers on the ground so far. So the ground truth is somewhat very limited. Such as limited the information that we have on rock composition. We have some hyperspectral data that provide us with some mineralogical hints, I call them, which is different from knowing the lithology. And somebody could argue that we cannot really speak of geological maps if we don't have information on lithology, because geological maps are based on Earth on lithological composition. On the other hand, we have a relatively limited weathering, and this allows a good preservation of the morphology. So this is different from Earth. And then there is all the problem of dating. Lucia already mentioned something about that, but also in the last days there were different things about this topic that will be addressed in a lecture this evening, so I'm not speaking about this. By the way, all this fact led to a traditional approach in planetary mapping, which is either chronostratigraphic or morphological rather than strictly geological, and then raises the problem of scale and equifinality. First of all, problem of scale as instrument dependent. We have here 3 images of the same area with 3 different data sets. This is HRSC. You see the resolution here, and we can see this landform. Basically, we see that this is a fan-shaped landform. We distinguish some light tone deposits, but that's it. If we move to CTX imagery, we can observe that this fan-shaped landform is actually made of more lobes. There are channels on top, and we can see that this light tone unit, we can observe there are some hints of layering here. If we move to high-rise resolution, we can see very clearly the layering, and we can observe the nature of the boundary between the 2 units. So, of course, all data sets are needed to understand the units, and maybe even more than boundaries. By the way, we need to use all the potential of all the data sets that we have. But at the same time, we must remember that the map must be consistent throughout all its extension, which means that we need to decide the scale of work before starting to map, in order to, one side, of course, fulfill our science goals, which are of course, the reason why we are starting, but at the same time, to keep the same detail on our representation. Just to make an example, we cannot map in one part of the area craters down to, for example, 100 meters of diameter, and in other part of the map, craters which have maybe 2 kilometers of diameter. So we must keep the map consistent. Okay. Then other problem, mapping scales and approaches in mapping. There are different ways to map, to perform mapping, and none of them is wrong. Always this method, these approaches depends on our science goal. We can use feature-based mapping when, for example, we are interested in observe the distribution of a specific feature. For example, we want to know deltas where are globally, or at least over very, very large areas. In this case, we just put a dot, maybe, on the place where these delta are. Then we can move to a more detailed area, regional to basin. In this case, we need to focus a map on the depositional environments. For example, channel, delta, lake. If we move even in more detail, so basin to some part of the basin, so we are interested in evaluating in detail the depositional environments, we have to go deeper and map the depositional elements. For example, in a delta, distinguish between delta plane, delta front, and prodelta. Needless to say, this last kind of mapping is possible only if we have high resolution data available, high rise, generally speaking. Otherwise, it's impossible. There is no one good way of mapping. It depends on our science goal. Other problem related to scale. In this case, we are focusing to the relation that we always have to make with Earth analogy, because in order to interpret our depositional environments or processes or whatever, we need to compare them to the terrestrial counterparts. And this raises problem. The first one is that we have here a map from Earth. This is Dallol, Ethiopia. This is Mars in Arabia Terra, Fears of Crater. If we look at the geological context at scales from the tens to the 100 kilometers, more or less, the scale is comparable. If we go into the detail, okay, we can see we have mounts on Earth and we have mounts also on Mars. Then we have polygonal pattern on Earth and we have polygonal pattern also on Mars, and the scale is roughly comparable. But on Mars, this is the maximum we can reach. On Earth, we can go into more detail and observe the detail of the facies, the dimensions of the cluster, in this case of the crystals, the nature, and whatever. So this is a problem in the analogy, which has a consequence in this other aspect, that is the problem of equifinality, because similar effects may be generated by different combinations of causative processes. Example, we have these mounts, again, the same mounts on Mars. Their genetic interpretation might be related to erosional remnants. So they might even be just not even the positional feature, just simple the result of differential erosion. Or they might have been formed as pingo, so in a glacial settings, or as mud volcanoes, or as spring mounds. So how can we cope with such problems? The only way is to integrate all the available data and define clearly a geological context. Defining a geological context means switching from the analysis of the single landform to the analysis of associated landforms, a landscape, which provides a tool to constrain the interpretation. In order to do this, we need to understand the lateral and vertical distribution of the different units, which means that we have to do the geological map and focus in doing that on the stratigraphic relations in order to understand which units are coeval. Then, of course, we will proceed with the interpretation. We will be able to proceed with a more constrained interpretation using the multiple working hypothesis approach, which has been fantastically described by Baker in 2014. It's one of the historical concepts on geology, but Baker wrote a fantastic paper on that, and by means of the analog studies. So this will work through the formulation of genetic hypotheses, several genetic hypotheses, then following of the consequences, and then testing this hypothesis again and again. So stratigraphy is important. I don't think I need to go into detail of the principle of stratigraphies, which are the basis of modern geology. They are the tool to order rocks and time, but I want just to focus a little bit on two ways of representation of the stratigraphic relations within a specific area. Two methods which are complementary in the sense that they provide informations, or better, they emphasize different information. In the diagram to the left is a space diagram. It's a diagram where we reconstruct the geometric relations between the different units. So here we have a crater margin. The crater is infilled with these impact breccia deposits. Then there is the deposition of these slumped evaporites. These two deposits, the breccia and the evaporites, are cut by this channel, which erodes these deposits and go later on there is the deposition of the material transported by the water inside the channel, this sandstone, and then all the basin is covered by this recent dust. So we have a succession of the events and the geometry of the different units involved. But all these dotted lines, they represent some time which is missing. And it's not very clear, this fact, when we represent it just with a line. No? We lose the concept of how much we lost here. So that's why that we use also, in addition to this space diagram, also a space-time diagram. Between the deposition of the deposits of the crater margin and the volcanic breccia, there is an interval with erosion and non-deposition, which means we are lacking sometimes. So in this diagram, we put the space here and the time in this direction. And we represent also the time that is not represented in my geological history, because the time that we miss is something that we must remember in our reconstruction. So we have time lacking here, we have time lacking between the deposition of the impact breccia and the evaporites, and so on. This conformable surface, the unconformable surface, sorry, are of different kind. We have, when we have, for example, sedimentary deposits lying on top of igneous or metamorphic basement deposits, this surface is called a non-conformity. If we have sedimentary deposits on top of which we have this surface with non-deposition and erosion, and then horizontal sedimentary deposits, we have an angular unconformity. If we have basically deposits with the same attitude above and below these deposits where non-deposition and erosion occur, we have a disconformity. When we have, the same attitude as before, but this surface measure a non-deposition, but maybe no erosion or very little erosion, this is, sorry again, a paraconformity. And then we have conformable layers with, there is continuity between the layers above and below. Oh, of course, this is something which is a matter of discussion, because our ability to understand non-deposition, the time that we miss depends also on our ability to resolve the time. But this is a topic that concerns more the paleontologist. For us, this works just perfectly. And this is an unconformity on Mars. This is a picture taken by Curiosity within Gale crater. You see these layers below. I hope you can see they are cut here. It means, maybe here is more clear, they are eroded in correspondence of this surface. So we have erosion, non-deposition, and then deposition of this other unit, formation in this specific case. To stress the fact that understanding and mapping unconformities is important, I would like to show, and also to connect to a question that was done to Lucia at the end of her presentation. I would like to show you this example from Eberswalde. Eberswalde, at those times, this is 2003, or now already an historical paper by Marin and Edgett, one of the first with the mock image, high resolution imagery that allowed to show this delta-like feature was called. This feature was considered the smoking gun evidence to prove the presence of persistent water flow on the surface of Mars, because, how one can contest that this morphology, look at this beautiful meanders and this chute cutoff here. How can one contest that this was formed by fluvial activity? And this was used to prove that water was stable on the surface of Mars for a significantly amount of geological time. But then olivine was detected in this crater. So somebody, I mean, olivine is not very consistent with the presence of water in a delta, because olivine is the first mineral to be degraded by water. So in a delta, I don't expect to have a delta or alluvial fan. There was a discussion. I will come back to that later. But if you go into more detail, this is one of the delta or lobes in any case, and even more detail. If we look at this succession, here we have two units, one light tone bedded units and a dark non-bedded unit. And we see that this dark unit rests on top of the bedded unit in different levels. Doesn't cover always the same horizon. It means that this level is a disconformity. It means that there is time between the deposition of the light tone unit and the dark unit, and in this time there was erosion and non-deposition. It means that these two units are two different parts of Mars geological history. And if we go and see the water abundance in correspondence of this crater, we observe that indeed the water abundance is maximum in correspondence of this light tone unit. Actually, it's not maximum, is present in this light tone unit, while is absent in this darker unit. It means that olivine-rich deposits lies above the disconformities and and they teach us a story which is different from the one of the light tone deposits. This part of the Eberswalde story is a part of the story with no water, but it has nothing to do with this part of the crater story. Speaking of beds, I want just to focus on one thing that is just only apparently formal. Because when we observe the beds, are we really sure that this is one single bed? Cannot maybe be a number of superposed similar beds, which on Earth we call bed set? We don't know, because our resolution isn't able to resolve something in more detail. So I don't want to say that we need to use the word bed set instead of bed or layer, because this is just terminology. It's not so important. I don't like to focus on formal stuff, but at the same time, we have to remember this in the sense that if we want to compare stratigraphic succession and the thickness of beds in different succession, we need to remember this in order to compare only succession where we have available data with comparable resolution, like these authors did perfectly. And again, speaking of beds somewhere terminate against something. This is another thing that is important in our stratigraphic reconstruction, because these terminations tell us something. Sometimes they are truncated, they are eroded. We just saw the unconformity. Truncation forms in correspondence of an unconformity. It means that there was no space anymore to accumulate these beds. Sometimes they are horizontal and they go to hit, so to say, a non-horizontal surface. This geometric fashion is called on-lap, and it means that I am filling the basin like this, poof, poof, always higher. It means I am filling the basin. The deposits are growing up vertically. Other geometry of lap. We have inclined beds like this, one beside the other, always forward within the basin. It means that the basin is infilled in this direction. I'm putting sediments inside the basin. This geometry is called of lap. These beds are called also clinoforms because they are inclined. And when they reach the base, this geometry, this fashion is called downlap. These names are not so important. The important part is to understand what do they mean. Filling the basin vertically, filling the basin in this direction. Top lap, it means that I am filling the basin in this direction, but I'm not filling this vertically. In this case, I'm filling the basin in both directions. In this case, I'm filling the basin only in this direction. But I have no erosion. All these geometries reflect a relation between sediment, which is delivered in a basin, and the ability of the basin to accept, to accommodate, we use this word, to accommodate this sediment. And this is very important in the stratigraphic reconstruction. Just to have some example, erosional truncation. We have here some light tone deposit. This is very similar to the surface we have seen before in Eberswalde. Light tone layer deposits here, which are cut. And on top of them, we have the deposition of these darker deposits. So here we have erosion and non-deposition. On lap, we have these horizontal strata, which are embaying horizontal beds. We are embaying this ridge, so to say, with this stratigraphic fashion. Maybe it's even clear in this image. This is an on-lap. These layers are growing vertically and hitting against, in this case, a crater wall. This is the fashion, stratigraphic, the reconstruction, the sketch of this geometry. This is an on-lap. Off-lap and on-lap. We have here an example from Curiosity, again, a picture taken from Curiosity within Gale Crater. This is Mount Sharp, and we observe these are clinoform prograding. You see these layers below are somewhat subhorizontal, and these layers are moving increasingly onward. Puff, puff. Other concept, which is not always easy to define on Mars, lateral transition. We have mounds here, some mounds and some layers, some beds. If we go into more detail, we observe that the layers continue from here, also inside of the mounds. It means that there is a lateral continuity between these two units or morphologies, whatever you want to call them. There is lateral continuity, which means that they are conform to Walter's law, one of the few laws in geology. It means that these deposits were coeval. They are part of the same history. And we have to recall this in our interpretation. Now, I want to go back to the different kind of map. I told you at the very beginning that historically, most of the geological maps on planet are chronostratigraphic maps. And this maps is the one of Tanaka that Lucia already showed you, that basically represents the age of the rocks and their classification in different phases of Mars history. This is the first tool that we use also on Earth to distinguish large units, geological units in large areas. Then we have geomorphological maps. Geomorphological maps are extremely interpretative maps. This is again Eberswalde. This is an extreme interpretative map. when we distinguished delta plane deposits, delta front, pro-delta deposit, and within the delta plane, for example, distributary channels, this meandering distributary channel, interdistributary areas, crevasses play. Of course, this is very interpretative. Geomorphological map. Each landform is associated to the interpreted genetic origin, to their interpreted genetic origin. Geological maps, okay, we have no lithological information. We stand always there. We have the exception of some hyperspectral derived mineralogical hints, but basically we don't know which rock is that. This is true. But on Earth, geological maps are intended to be the most objective, between brackets, tool that we have to map our area. While objective, because lithology is something, I mean, a rock is a rock, no? Of course, there are matter of discussion, but everything is structured in a way to be as objective as possible in order to be the basis of all the future analysis. So we could translate this concept on Mars, like on Mars, but this is true even for other planetary body. Okay, Mars is easier because we have high resolution data more than in other planets, but okay. You need to define on the basis of as objective characteristics as possible, as the color, the texture, the fact that they are layered and non layered, there are sedimentary structures or not, which kind, at all scales. I wrote here high-rise and CTX, but actually this should be done at all available scale. And also morphologies, but morphology is not intended with their interpretation, no? For example, a ridge, not a channel, just their shape. So no interpretation, but their shape. The shape is something that is an objective stuff. At all scale, of course. Thicknesses, erosional, depositional geometries, whatever. And of course, always stratigraphic position within the succession, like in all geological maps. And this is an example. This is again Eberswalde. And the map is very different from the previous one, because here we mapped the unit trying to be as objective as possible. No interpretation, just a substratum, massive rocks. We tried it even to formalize a formation. This is not so important, but the light tone unit, we distinguished between a layered member and a non-layered member. And then the dark unit we saw before. And there is a non-conformity between the substratum and the light tone deposits, and this is the disconformity we saw just before between the light tone deposits, layered light tone deposits, and the darker units. This definition is as objective as it is possible to do. In this specific crater, we could go even in more detail, because it is possible to go even more detail because of the data available, and it is possible to realize a sort of facies map. Maybe facies is a bit improper term used on planet, but still, the light tone deposits have been divided in three, let's call them facies. Medium rough texture, this one, breccia, and polygonal pattern. This medium rough texture, this orange, and then this breccia is here, and then we have the polygonal pattern unit. Again, these characteristics are characteristics that can be objectively observed. So there is no interpretation in here. This should be actually the base to realize later a geomorphological map with interpretation of the genetic origin of these rocks. Whatever kind of map we are approaching to do, a good thing to do is to start with a stratotype. Okay, stratotype on Earth are something which are formally defined. And there is all a long story of preparing and realizing this, describing this stratotype. But basically, it means something very simple. It's a physical place that serves as a standard of reference. So if I want to map in a specific area, I can go to the stratotype and look at my unit. And in Italian, we say make the eye, to understand how this unit looks like, and being able to map this unit also elsewhere, maybe where the outcrop conditions are not as nice as in the stratotype. And of course, this is the first thing that we have to do before starting to map, because we cannot map, of course, what we do not really know what it is. We can do something very similar even on Mars, even on the planets. It's even if it's not a formal procedure, we can find a place where our unit at all scale is best preserved. For example, again, I'm sorry, the same example of Eberswalde, but it's a nice example to show all these characters. Let's start with the HRSC data. HRSC data, and let's also again focus on these light tone units. Basically, what we can say that this unit is associated to a fan-like landform. It's only distributed in correspondence of the landform. We can observe some layering maybe, but not so much more. We move to CDX. In CDX, we can see that this unit is actually rugged. That is, of course, light tone, that is layered. And we can see that it's covered by the dark tone deposits. We can see also that it is onlapping against this very rugged unit. If we move to high rise, we can observe the nature why this unit is actually rugged here, because it's rugged elsewhere for different reasons. By the way, here is because it is disrupted in a polygonal pattern. And we can observe much better the nature of the contact between the light tone unit and the dark tone deposits. And we can observe that this is actually disconformity. Of course, it would be fantastic to have a ground truth example by a rover, in situ rover, with a section measured just like we could be there in front of the outcrop. This is already an historical example by Grotzinger et al. In 2005. The image was taken by Opportunity. We have here cross-bedded strata of Aeolian dune origin, then this flat-bedded layers, which has been interpreted as an Aeolian sand sheet, and here interdune playa deposit with this gypsum presence. We would not need to have all, of course it would be fantastic, but it is not necessary to have all our area covered by this detail, but it would be fantastic to tie the remote sensing based map with this data. This is something that it is possible now to do, but just in very few spots where, again, we have rovers on the ground. Now, I'm going to speak a little bit on some of the sedimentary systems on Mars. Just some example. I'm sorry, there is, I mean, it would be an entire course to speak of all the sedimentary systems that have been described on Mars, but I will stick to the fluvial lacustrine deposition environments and the light tone deposits, because they are the one more interested by studies on habitability. They are interested by the landing site missions. They describe that part of early Mars, which is probably the most interesting. And the outflow channel, because they are very important from an historical point of view, because they represent one of those cases where Martian study helped to better understand terrestrial studies. First of all, sedimentary basins are low areas where in the crust where sediments can accumulate. And instead on Earth, basically all the basins, almost all the basins are related to subsidence formed by plate tectonics. On Mars, the most important basin forming process is impact cratering. In order to have deposition environments, the step is this one. We start with the processes of transport of these are aeolian processes and deposits. We have processes class that are transported by different means in suspension, saltation, reptation. Ultimately, they form a landform, in this case, a dune. This dune, and this is a different with this part is basically the same on Earth and on Mars, with the difference, of course, related to difference gravity and atmosphere, very conditions, but the kind of processes are the same. The landforms on Earth are something which are geologically short-term, which means that basically we have landforms preserved only in the Quaternary, on Earth. This is not true on Mars because since the weathering is not as effective as on Earth, we can have morphologies that are even billions of years old. That's why I'm also speaking so much about stratigraphy, because morphology on Earth is something that yes, a bit, of course, with stratigraphy, but not so much, because it deals with short-term stories. On Mars, we deal with long-term geological histories. The association of these landforms, of what remains of this landform, because these are fossil dunes which have been, what's left of dune, because have been subjected to partially to erosion and deposition of other dunes, a stacking pattern of different dunes, form a deposit. And these deposits are both long-term geological story, both on Earth and on Mars. But of course, it's complicated to see them on Mars, because in order to see them, we need outcrops, which means that we need erosion and exhumation, because from above, it's impossible. If we look from here, we can see only this surface. So this is a problem on Martian study. Ideally, landform, we use landform to form, to draw geomorphological map and deposits for geological maps. But we saw that the distinction is sometimes not so strict. By the way, fluvial casting deposition environments, again, I will be very sketchy here. Main depositional elements, we have alluvial fans, we have very different kind of channels and valley networks, we have deltas, and we have casting systems. Alluvial fans are the relatively steep cones that form, consist the most proximal alluvial deposition environment. They form generally, but I will show that there is also an exception, but generally they form at the break of slope at the edge of a floodplain. Basically, when the bedrock river, here we have a mountain on Earth, maybe a crater rim on Mars, and we have bedrock river. What does it mean, bedrock river? It means rivers which are justly eroding. So features that not leave the position, so they do not contribute to the stratigraphic record. Alluvial rivers are those rivers that, of course, first they erode, but then they deposit material, so they contribute to the alluvial record. And when this bedrock river reach the plain, they lose competence and deposit material. This is an alluvial fan on Earth in the Death Valley, and this is an alluvial fan on Mars. This is Holden crater. This if you look at the profile is relatively constant throughout all the topographic profile of the fan. Just to mention, if we have several juxtaposed alluvial fan, we have a bahada or an apron. We have many of those on Mars. When the bedrock river enter a standing body of water, we have a fan delta, a sort of mixture feature between an alluvial fan and the delta, because it's fed by bedrock river, but it enters like an alluvial fan, but it enters a standing body of water, sorry, like a delta. So that's the mixed name, fan delta. Then there are also specific particular fans, which are called terminal fans, which form not because there is some topographic break, but just because the river lose their ability to transport material, so their competence, because of evaporation or infiltration. Basically, they lose water, so they cannot transport sediment anymore. Needless to say, these kind of features occur in arid settings. This map is interesting because also it represents an example of feature-based mapping. Here we have a representation of the valley network, and here we have all kind of channels, river, bedrock, and alluvial channels. Is not important. In this case, the authors wanted just to draw all the channels, the fluvial channels, also in order to understand and to constrain the possibility of an existence of a putative, there is a big discussion of the possible existence of an ocean on Mars. Elevation for this ocean has been proposed, but it's very difficult to prove, sedimentologically speaking, to prove it, because beach deposits are very easy to be eroded. So it's difficult to find proof, sedimentary proof of its existence. So indirectly, these maps address one point. I mean, this valley network appear to stop more or less in correspondence of these two possible coastline. Okay, dependence of this science topic, this is the distribution of valley network on Mars. It's, you see, they cover almost entirely the highlands. This is an example of valley network and of a single channel. Of course, these are not the same stuff, because valley networks requires the interplay of different valleys. A specific case that is worth to be mentioned is of channel is the sapping channel. The sapping channels. The sapping channels are formed by the erosion of groundwater. They are very characteristic because they have this amphitheater head like valley, which are, I mean, very easy to recognize. This is Earth, of course. This is Utah, and this is Mars, an example of this kind of valleys. Alluvial rivers are present in the alluvial plains. So we have channels. This is an example. Meandering channels are the most common among, so to say, the most commons on Mars, and they are surrounded by interdistributary areas, interchannel areas with levees, crevasse plains when the flood break the levees and deposit material in the floodplain, and the floodplain is the surrounding areas which is fed only during the episode of flood by finer grained material. In general, all the interchannel areas are characterized by finer grained material, which means that these materials are easier to be eroded. So that's why on Mars we have very often this kind of story. Basically, we have once the evolution of this channel and floodplain system ends, erosion starts to act. And of course, even just aeolian erosion is much more effective on these finer grain deposits than in these coarser grain soil again, which are sandstone or maybe gravel deposits, so are very difficult to be eroded by wind. So with time, what is called an exhumed channel is formed. This is an example from Earth, from Utah, and this is a beautiful example from Mars. This sort of beautiful snake is actually an exhumed channel in Aeolis dorsa, and it represents a exhumed channel because the floodplain material which was here has been swept away, and this remains in this so to say elevated position. Then I would like to show you this because just to speak about the deposits and the difficult to see deposits on Mars, this is a lucky spot close to Hellas in this area. Here there is this topographic break, very large, where this stacking pattern of channel have been described recently. This is a paper from last year. So this is an example of many channels which are embedded, actually stacked one on top of the other. A beautiful example which gives you the idea of the complexity of this system. Complexity that from remote we can just, I would not say guess, but of course we cannot fully understand, unless in a situation which is as lucky as this one. This is a stacking pattern of channels on Earth, just to show you the similarities between these two geometries. Deltas, okay, finally, our bedrock river or alluvial river enter a standing body of water. So we will have a fan delta or a delta, depending on which of these two. Deltas have a delta plane, a delta front, and the prodelta. Delta plane, we have the fluvial system, which assume a distributary pattern. In the delta front, there is the interplay between the process related to river distribution and wave reworking. These processes led the delta to assume a topographic break here. This is important because this topographic break is something that we can recognize even remotely. For example, here, always in Eberswalde, there is a topographic break. So we have delta plane, delta front, prodelta. This is just zero crater where Perseverance is going soon to land. And here we can even observe an example. Look at this. This is probably the figure where it's more clear. You see these layers, inclined layers, so clinoforms, which prograde with an off-lap geometry on top of this horizontal beds. It means that we are feeling the delta is moving inside the basin, feeling the basin. This is Sabrina Wallis, and this image is to show you another example of delta, but especially to show you again this topographic break, which allow us to tell that this feature was actually a delta, not just a simple alluvial fan. And this is also constrained by the fact that we have a flat area inside the crater. I will come to this in a while. Channel, delta, flat area. So association of laterally landform and associated landform. So the interpretation is much more constrained. Lacustrine systems, it's very difficult to look for coastal systems in lakes because they are relatively poor developed even on Earth. I mean, if you want to go to the beach, you go to the sea, to the lakes, I mean, you have very small spots. Moreover, the coastal deposits are very easily eroded. So there are some terraces sometimes, but they are not as distributed, as preserved as we would like. So we don't have so many distinctive geomorphological elements that allow us to prove, yes, we are in a lake. Okay, flat basin floor, this is true, because deposits which drape inside the basin provide this geometry, but the geomorphological elements within lakes are not so many. This, by the way, this is an example. We are again in Gale crater, and this is the base, the flat base of the lacastering system there. And here you can see the prograde incline of form the off-flap geometry in Mount Sharp here. Just a few words on the catastrophic flow. First, on Earth. The example of the catastrophic flow on Earth, of course, is the Pleistocene flow of the channeled scablands, which is the one represented here in yellow. I suppose all of you heard of it. Is very famous, formed by the advancing of the ice sheet during the Pleistocene, which blocked the drainage of this river, led to the formation of a lake. When this ice sheet started to retreat, the water of the lake dramatically, catastrophically, better to say, formed these huge floods, gigantic flow, I would say. And this flows inside the loess deposit here, but also basaltic flow. This by these turbulent flows, 100 meters deep, and form this characteristic geometry. This is an example of the bedrock. This is a clast. Giant current ripples. I mean, you see the scale. You can guess the scale from here. And this characteristic flat base of these huge valleys, which are deeply incised by these inner channels, and then you have these lakes which were formed by the turbulent erosion. On Mars, these features are huge as well, large-scale channels. There is the sign of multiple episodes of catastrophic floods, or sometimes just one flood. This is the place where they are mostly concentrated. They are often associated to chaotic terrains. If you go to have a look to an example in Ares valleys, we see that the morphologies are very similar to the one on Earth. This is actually the morphologies are much better preserved on Mars than on Earth, because of course on Earth erosion and weathering already started to destroy some of these morphologies. That's why I was mentioning that this kind of features help to found many other catastrophic features on Earth, in Patagonia, for example, in Siberia, in the English Channel. This is a profile, topographic profile, just to look to show you the topography very similar to the one we saw before on Earth. Look at the scale. The scale is again huge. And on Mars, these channels appear to originate from chaotic terrain. So the water seems to source from the groundwater. Now, if I have time, I quickly tell you something about the light tone deposit, which are thick layered material up to several kilometers thick material, with a very different distribution, very thickness. They are important because they are associated to hydrated minerals almost always. They are located inside ice crater infill in the chaotic terrain and inside Valles Marineris, the famous interior layer deposits already introduced by Luchita in the 90s. These are the interior layer deposits you see. this thickness can reach up to 7-8 kilometers, so a huge stuff. And the layers appear to drape and dip outside of these buildings. In the chaos, they are much more localized, much less thick than in Valles Marineris, and they postdate the chaotic terrain formation. While in the craters, they have this, again, they are less thick than in Valles Marineris, but thicker than in the chaotic terrains. They are like this. This is the average scale you can observe. Sometimes they are associated with these mounds. The genetic formation of these deposits is still under debate. Probably is an interplay between aeolian deposition and some spring deposits contribution, both to cement the aeolian deposits, but also to form some of these landforms. But I wanted just to stick 1 second in the geological map of this area, because here there is a reconstruction. The layer deposits are this one in yellow, the mounds in blue, yellow and orange outside of the crater, because they are a little bit different. And this is a geological section to express the geometric relations between the bodies. So these are the layer deposits. The base of this section has been interpreted using Garvin equations, so the thickness is more or less real, at least the magnitude order. And this is the space-time diagram, which allowed to tell that the different layer deposits are represent a phase in the history of this basin, different from the time separated from the units that stay at the base at the top of this unit. Now, I don't think I have to, since it is a little bit late, I don't want to go and repeat things that I told already. So I want just to finish telling that, emphasizing again the role of stratigraphy, which is very important. It's always important, but it is especially important when you are dealing with sedimentary systems. I hope that this message was clear enough. Thank you for your attention and your patience.
Thank you, Monica. We have some minutes for potential questions, so I would ask if someone wants to ask something. And there are actually questions during your presentation. Yeah, I'm looking there.
I am looking at.
And there are, how is the way to measure strike and dips of sedimentary sequence deposit strata?
Okay, this is something that you can do when you have a good DEM and also good imagery, because basically the idea is the layers are the intersection between the layer and the topography. So there are tools that allow to you draw the map, the bed, and you see the geometry of the correspondent plane. There are tools that can be used with different softwares. During our job, we use one software which is called Orion. I don't know if I can make it. It's not commercial. But you have just to pay attention. It's just the geometric relations between the horizontal and the bed plane. You have to reconstruct that. Of course, it's a little bit more complicated to use the compass in the field, but it's the same concept.
Yes, the 3 points method. If you are able to see the strata, you can use the 3-point method. All this software works according to that philosophy. And then there is another interesting question, I think. Is there an example of Martian sedimentary record that is not completely analogous with the terrestrial ones?
Well, actually, completely analogous we have never a complete analogy. For example, outflow channels are very similar to Earth, but they are bigger. Everything on Mars looks huge. And the same, the layer deposit, the last one I show you, is something that is still under debate, but probably it's a mixture of processes that on Earth we see only locally, only in a few spots, or maybe in different part of our geological record. We don't have a present or very few present analogy to these systems, but the basic processes are the same. Of course, in different conditions. The basins are different, for example. This is the first thing. So also the relations between the sediment input and the accommodation is different than on Earth.
Then there is another questions about Jezero. What are the study of perseverance on Jezero Delta that you are looking for most? So it could be the most interesting, I think, that are foreseen by perseverance. I think this is the question.
Well, perseverance is, I mean, the main goal is to look for habitable conditions. But I think that the most important stuff will be to compare, but more or less like they are doing on with curiosity data, to compare what we can see from remote sensing to what we can see in situ. This is very interesting from a methodological point of view, because it will teach us how to interpret and which are the limits of our interpretation from remote. It's always very difficult, no? When you're working from remote, sometimes you think you can say something, sometimes it is difficult to constrain and tell where is my limit. So in situ data will help us to really tie the remote sensing work with the in situ data. From the specific point of view of the crater, we will learn much more about the depositional processes and the timing. This is another big topic I didn't speak about. There was, for a long time, we thought that the water-related deposition on Mars was episodic and brief. It looks like it was not really like that. The figure I saw from that paper where there is this large outcrop, it shows a very complex geological history. So this data will be very important to constrain that. And then, of course, there is all the discussion of habitability. This is more a topic for biogeologists. They are looking for possibility for life, which of course would be a revolution, from also philosophical revolution.
So I would say there is, you have already answered to one questions about sustaining flow or episodic ones in Jezero. So there is the last question here is the terrestrial analogs for knobs, small hills that you have shown in your talk.
The one that I show the picture it came from.
It's the fierce of one, I think.
Sorry?
It's the fierce of picture.
Ah, okay, okay. The terrestrial analog. I show a picture on terrestrial analog as erosional remnant, and that specific picture comes from, I don't remember where, in which park of the United States. It should be written in the presentation, but the fears of picture, the discussion is still open. Are there knobs, so erosional remnant, or are they depositional feature? This is a completely open topic, in the sense that there are many evidences that this feature were originated from fluid upwelling, so they are not erosional remnant, but depositional features originated by fluid coming from the subsurface and precipitating material once reached the surface. I don't know if I really answered that question.